Hello, myself Shubhashish Shah, Assistant Professor of Mathematics of Greater Kolkata College of Engineering and Management, GIS School. In this video, I will discuss about sequence in real number. And the name of the subject is Mathematics 3. Subject code is Mathematics, BSC301. This subject is for the students of Computer Science and Engineering and Information Technology. Module number is 1. And this subject and this syllabus is under MacOut. Okay. So in this module number 1, you have the first chapter as sequence and series. Okay, and I should tell you that in the previous years in the examination, most of the questions have come from the part series, but we have to learn sequence to know what is series. So in this video I will tell you something about series, and this is a huge chapter. Many things to say about sequence, but I will try to cover maximum part of this sequence in this video. Okay, then in next video I will discuss about series, which is important for your examination. Okay, so what is the definition of a sequence? Sequence actually is a mapping. Sequence is a mapping. Okay, a mapping from natural number to real number. A mapping or function, you can say function, from natural number to real number is said to be a sequence in real number, or you can say it as a real sequence. Okay, so sequence is nothing but a mapping from natural number to real number. Okay, so a sequence is generally denoted by like this: fn within a second bracket, that is f1, f2. Since the domain set is natural number, so n comes from natural number, and that is f1, f2, f3 ... So it will be defined, the mapping will be defined when I will give you examples. Okay, so you can denote a sequence by this, or like un or like vn. Okay, in such ways. Okay, so now I'll give you some examples of sequence. First example is, let f natural number to real number, that is the function fn to r, be defined by fn equal to n, where n belongs to natural number. Okay, so this sequence will be denoted by as this. This will be denoted by n. This sequence will be denoted by n. Okay, or you can also denote it by 1, 2, 3 ... That is, for f1 it will be 1, for f2 it will be 2, for f3 it will be 3. So the images you can write for denoting the sequence. Okay, so next example, fn equal to n square. Okay, fn equal to n square. I am not writing this. The function is from natural number to real number. I have already told you. This is the definition of sequence. I am just writing the definition of the function, and this sequence will be like 1 square, 2 square, 3 square, dot dot dot. Okay. Now one more example. If natural number to real number is defined by if n equal to n by n plus 1. Okay. So what will be the sequence? It will be like 1 by 2, that is 1 plus 1. For f2, for n equal to 2, it will be 2 by 3, 2 by 3, next 3 by 4, like this. Okay. Now next example, number 4. If n to r is defined by if n equal to minus 1 to the power n. So the sequence will be like minus 1. For n equal to 1, this will be minus 1. For n equal to 2, this will be plus 1. And like this, it will continue. Minus 1, plus 1, minus 1, plus 1. Okay. Okay. I'm removing this. Next, example number 5. If n to r defined by if n equal to sine n pi by 2. Okay, so this sequence will be like, first for n equal to 1 it is sine pi by 2 and that is 1. For n equal to 2 that is sine pi is 0. Okay, next for n equal to 3 sine 3 pi by 2, that will be minus 1. Again it will repeat 1 0 minus 1. It will continue like this, and obviously these are all infinite sequence. Okay, this will continue infinitely. Okay, next example. If natural number to real number is defined as if n equal to 2, if n equal to 2. So this sequence will be denoted by 2, 2, 2, 2. Dot dot dot. This sequence is called constant sequence because all the for all real number, natural number, the images, the elements of the sequence will be 2. So this is constant. So this type of sequence is called constant sequence. Okay. Now I'll tell you some definition, some properties of sequence. Number 1, a real sequence is said to be bounded above, if there exists a real number, capital G, such that Fn less than equal to capital G for all n belongs to natural number. Okay, so then G is said to be bounded above. That is, G is such a real number for which all the elements of the sequence, Fn means for all n belongs to natural number, here it is written, that is all the elements of this sequence will be less than or equal to that real number. If this type of number exists, real number exists, then this sequence will be called bounded above, and G is said to be the upper bound. G is said to be the upper bound. Okay. Next, number 2. Similarly, we can define a bounded sequence is bounded below. A real sequence is said to be bounded below. Same definition. If there exists a real number small g. Okay, I am not writing here. A real sequence is said to be bounded below. Okay, I am writing BDD for bounded below. Okay, if there exists a real number small g such that Fn will be greater than equal to g for all n belongs to natural number. Okay, and G is said to be the lower bound. lower bound. So if there exists a real number small g for which all the elements of the sequence will be greater than or equal to that real number, then that sequence is called bounded below, and g is obviously said to be the lower bound. That is, these are the elements of the sequence, and this is small g and this is capital G. So all the elements of the sequence are less than equal to capital G and greater than equal to small g. So obviously G will be the lower bound and capital G will be the upper bound. Okay, if capital G exists, then the sequence will be called bounded above. If small g exists, then the sequence will be called bounded below. Okay, now if a sequence is bounded below and above both, if bounded below and above both, then the sequence is called only bounded. Then the sequence is called only bounded. So if I'll give you the examples of bounded sequence. First I write the definitions, then I will give you example. So if a sequence is bounded below and bounded above both, okay, that is small g and capital G both exist. That is small g less than equal to fn less than equal to capital G for all n belongs to n, then the sequence is called bounded sequence. Okay, so if the sequence is bounded below and above both, then that sequence fn, we can denote it by fn. Fn will be called bounded sequence. Okay, next I will go to the next definition: least upper bound or supremum. Least upper bound or supremum. This is very important. Okay, I am removing all these. Least upper bound, or it is called as LUB or supremum. Okay, or supremum is denoted by as sup of Fn. Okay, so what is the definition? The LUB, that is least upper bound of a real sequence Fn is a real number, capital M, say, satisfying the following conditions. Okay, satisfying the following conditions. Now I will write the conditions. Condition number one, Fn will be less than equal to capital M for all n belongs to natural number. That is, all the elements of the sequence will be less than equal to that real number. Like, that is, the LUB is an upper bound. Okay, should be an upper bound, must be an upper bound. And condition number two, for each pre-assigned positive epsilon, there exists a natural number k such that Fk greater than m minus epsilon. Okay, so the condition number two states that if you decrease this m by some very small positive quantity, then some of the elements of the sequence may be greater than that resulting quantity, that is m minus epsilon. So that does not remain the upper bound. That means capital M is the least upper bound. No upper bound exists which is less than m. So m is called the least upper bound or supremum, or it is denoted by supremum Fn. Okay, so this was the definition of least upper bound. Similarly, there may exist a as we have studied the lower bound, so the greatest lower bound. Okay, so greatest lower bound, least upper bound and greatest lower bound. Now I will tell you the definition of greatest lower bound. Okay, so greatest lower bound, it is denoted by GLB or infimum. It is called also as infimum and denoted by INF of Fn. Okay, so now I will write the definition of this greatest lower bound. So the GLB of a real sequence Fn is a real number small m, say, satisfying the following conditions. Okay, so condition number 1 is Fn will be greater than equal to m for all n belongs to natural number, that is m is a lower bound. M must be a lower bound, that is all greatest lower bound or infimum is a lower bound. And number 2 is there for each pre-assigned epsilon, for each pre-assigned positive epsilon, there exists a natural number k such that Fk will be less than m plus epsilon. That is, first of all, m should be the lower bound, and such a lower bound that if you add some very small positive quantity with m, then some of the elements of the sequence will be less than that resulting quantity, that is m plus epsilon. So m plus epsilon does not does not remain the lower bound. So m was the greatest lower bound. Okay, now I will give you some examples of this supremum, infimum, upper bound, lower bound. Okay, so before giving the examples, 2 things I should tell you. A real sequence Fn is unbounded above. I have told you the definition of bounded above and bounded below, and now I am telling you the definition of unbounded above. So if the Fn is a real sequence is unbounded above if supremum of Fn is infinite. That is upper bound. If the upper bound is infinite, least upper bound, the supremum is infinite, then the sequence will be called unbounded above. And similarly, a real sequence Fn is unbounded below if infimum of Fn is minus infinity. Okay, sorry. So unbounded above means supremum is plus infinity, and the unbounded below means infimum is minus infinity. And the sequence will be called unbounded if it is both unbounded above and unbounded below. Okay, so now see the examples. First example I'm giving you is the sequence, real sequence 1 by n. Now this sequence is bounded. Okay, what is the supremum and what is the infimum? The supremum of this sequence is 0. That is okay, first I write the infimum. Supremum is 1, infimum is 0. Infimum is 0. Okay. So next example is n square. Okay, so n square is, we can't say that n square is bounded because it is not bounded above and bounded below both. Okay, it is bounded below, but not bounded above. Okay, because supremum of this sequence is infinite. Okay, and infimum is 1. Infimum is 1 and supremum is infinite. Okay, so if you write the elements of the sequence, then you can understand. First element will be 1 square, 2 square, 3 square. So it is clear that supremum is infinite and infimum is 1. Okay, next example, minus n square. Minus n square, like the previous example, we can see that it is bounded above but not bounded below. It is not bounded below because infimum is minus infinity and supremum is minus 1. Okay, so since supremum exists, finite supremum exists, so this will be bounded above. Okay, so next example is, I am writing here example number 4. Okay, minus 2n. Okay, now you see that this sequence will look like minus 2. Okay, first if you write the elements, some of the elements, then you can understand that this sequence is bounded above or bounded below or bounded. So minus 2, next will be minus 4 for n equal to 3, this will be minus 6 dot dot dot. Okay, so you can see that this sequence is bounded above but not bounded below, because it will continue like this and there will be no lower bound. So infimum is minus infinity and supremum is minus 2. So we can say that this is bounded above but not bounded below. Okay, next example, minus 1 to the power n. Minus 1 to the power n. Now see, the elements of the sequence will be minus 1 plus 1 minus 1 plus 1 minus 1 plus 1, like this. So it is clear that this sequence has both supremum and infimum. So this sequence is bounded. So supremum is plus 1 and infimum is minus 1. Okay. Okay. Next example. Example number 6. Minus 1 to the power n into n. Okay. So I write first the elements of the sequence. First element will be minus 1. For n equal to 1, this will be minus 1. For n equal to 2, this will be 2, then minus 3, then 4, minus 5, like this. Okay. So see, this sequence, for the negative integers it is going like minus 1, minus 3, minus 5, minus 7, like this, and on the positive side, on the real number, 2, 4, 6, 8, 10, like this. Okay, so this sequence is not bounded because there is no upper bound and no lower bound. Unbounded sequence. Unbounded sequence, because supremum is plus infinity and infimum is minus infinity. So this sequence is unbounded sequence. Okay, next I'll tell you the definition of limit of a sequence. Limit of a sequence. Limit of a sequence. So the definition is, let Fn be a real sequence. A real number L is said to be a limit of the sequence if corresponding to a pre-assigned positive epsilon, there exists a natural number k such that mod of Fn minus L less than epsilon for all n greater or equal to k, or you can say that L minus epsilon less than Fn less than L plus epsilon for all n greater or equal to k. So this was the definition of a limit of a sequence. I'll give you example. Before that, another definition, is convergent. This is very important. Convergent sequence. Okay. So a real sequence Fn is said to be a convergent sequence. Okay, I'm removing this and I'm writing here. A convergent sequence if it has a limit L belongs to real number. In this case, the sequence is said to converge to L. So if limit n tends to infinity, Fn equal to L, then we say that the sequence Fn is convergent and it converges to L. Okay, so L should be a finite real number. Now I'll give you some examples of convergent sequences. Number 1, the sequence 1 by n. This sequence converges to 0 because limit n tends to infinity Fn, that is 1 by n, is equal to 0. So the limit of this sequence exists, there is finite limit, and so this sequence is convergent to 0. This is a convergent sequence. The second example is n square plus 1 by n square. So this sequence is convergent or not. To test that, we have to find that this sequence has a finite limit or not. Okay, so limit n tends to infinity n square plus 1 by n square equal to limit n tends to infinity n square plus 1. Okay, so we are dividing by n square in the denominator and numerator, so it will be 1 plus 1 by n square by 1. If we calculate this, for this part it will be 0, so the result will be 1. So this sequence has a finite limit 1, that is 1, so this sequence is convergent sequence and converges to 1. Okay, so the next example number 3, the sequence 2 2 2, I told you that this is the constant sequence. So obviously this sequence is convergent sequence and converges to 2. Okay, so constant sequence is always convergent and converges to that constant. Okay, so next we take the sequence -1 whole to the power n, that is the sequence -1 plus 1 minus 1 plus 1, like this. So this sequence is not convergent because no finite limit exists for this sequence. So this sequence is not convergent. So this sequence, we know that this sequence is bounded. Okay, this sequence is bounded but not convergent. So a convergent sequence is always bounded. But from this example we can say that a sequence may be bounded, but bounded sequence may not be convergent. Okay, as this is bounded but not convergent. Okay, so this is a very important result. Now I will give you some sequence and you will try it to find that these sequences are convergent or not. Number 1, number 2, n square plus 1 by 2n square plus 3, and number 3, n square minus 1 by n square plus n plus 1. This is your assignment for home. You will try to find that this sequence are convergent or not. Now the next definition I will tell you. A sequence Fn is said to properly divergent if it either diverges to plus infinity or diverges to minus infinity. So a sequence is said to be properly divergent if it either diverges to plus infinity or diverges to minus infinity. Now a bounded sequence may not be convergent. Okay, we have seen it before. A bounded sequence that is not convergent, is said to be an oscillatory sequence of finite oscillation. So those type of sequence which are bounded but not convergent, I gave you an example. So those type of sequence are called oscillatory sequence of finite oscillation. Okay, now an unbounded sequence that is not properly divergent is said to be oscillatory sequence of infinite oscillation. Now I'll give you the examples of these definitions. So the examples are: number 1, 2 to the power n. This sequence diverges to plus infinity, diverges to plus infinity. It is unbounded above. So this sequence can be called properly divergent. Okay. Number 2, minus n square. So minus n square diverges to minus infinity. So this sequence is also properly divergent because the terms of this sequence will be minus 1 square, minus 2 square, minus 3 square. So this will be bounded below, and the infimum will be minus infinity, that is bounded below, unbounded below, unbounded below. So it diverges to minus infinity, and this sequence is properly divergent. Number 3, minus 1 to the power n. Okay, this sequence is look like minus 1 plus 1, minus 1 plus 1. I have discussed about this sequence, and this sequence is bounded because supremum is, this sequence is bounded. We know that supremum is plus 1, infimum is minus 1. But we have seen that this sequence is not convergent. This sequence is not convergent. So I just told you a bounded sequence which is not convergent is called oscillatory sequence of finite oscillation. So this sequence is an oscillatory sequence of finite oscillation. Okay, so this was an example of oscillatory sequence of finite oscillation. Now minus 1 to the power n into n. Now this sequence is first element will be minus 1, then 2, minus 3, 4. I have also given this example before. So this sequence is unbounded. Clearly it is unbounded. Infimum is minus infinity and supremum is plus infinity, unbounded above and below both. Okay, but it is not properly divergent. It is not properly divergent because it is the infimum is minus infinity and supremum is plus infinity. That is, the sequence is bounded below, unbounded below and unbounded above both. Okay, so this sequence is not properly divergent, not properly divergent. And unbounded. So I just told you the definition that an unbounded sequence but not properly divergent is said to be oscillatory sequence of infinite oscillation. So this was an example of oscillatory sequence of infinite oscillation. So this was all for this video. I have briefly discussed about a basic concept of sequence. In next video I will discuss about series, and the knowledge of sequence is very much needed to learn series. So this basic concept of sequence should be known to you. Okay, so you watch this video, and if you have any query, then you can contact with me. My contact details is given in the first slide of the video. Thank you.